Here we are on page 3 of the HL Vector Apps addendum. The first thing is we're going to do a problem from 15D. This problem is just a little bit different because it gives one of the lines in Cartesian form. So let's see how we treat this differently. We want the angle between the lines. Normally, what we do is we take the direction vector of each of the vector equations, and then we use those direction vectors to find out the scalar product, and through that we could figure out what theta is between the two. But where is the direction vector here? There is none. So what we can do is we could take our Cartesian form here and we can make it back into parametric form. So we could say that, we could say that, and we could say that. So we could go backwards and make the Cartesian equation into parametric form. So we could have 3 lambda plus 8 equals x. And we could have 16 lambda minus 9 equals negative y. And we could make everything the right sign by saying 9y equals negative 16 lambda plus 9, and we could say that 7 lambda plus 10 is equal to z. And so now we're going to rearrange it into a vector equation. X, y, z is equal to the position vector 8, 9, 10 plus the direction vector 3, and I'm just taking the multiplier of each lambda here to find the direction vector. It would be 3, 16, 7 would be the direction vector times lambda. And so now what you would do is you would just take this direction vector and scalar product with that direction vector. So you would have 3, 16, and 7 scalar product with 3, 8, negative 5, and that would be equal to the magnitude of this vector times the magnitude of this vector times the cosine of theta, right? So we could say cosine of theta is equal to 3, 16, 7 dot product 3, 8, negative 5. I'm going to dot product those together, and then I just take the magnitudes of each one and divide it there, and that will give me a proportion. Okay, so the scalar product of 3, 16, 7 and 3, 8, negative 5 would be 9 plus 128 plus or minus 35. So that would be the numerator. The denominator would be a huge mess. It would be 3 squared plus 16 squared. Gosh, terrible writing. Okay, 3 squared plus 16 squared plus, 7 squared times 3 squared plus 8 squared plus 5 squared. Okay, so, wow. Let me calculate that and I'll get back to you. So actually, remember that this is negative 16 lambda, so this should actually be negative 16. This should be negative 16. As a result, when you take the scalar product, negative 16 times 8, you should get negative 128 here. So when you multiply out the top, or subtract out the top, you end up with 154 on top. And then on the bottom, if you multiply 314 times 98, and then take the square root of that, you end up with 175.4 on the bottom. And that gives you a ratio of 0.878. And then if you take the inverse cosine of that, that gives you an angle of 28.6 degrees. Okay, so that is the answer. Oops. Okay. 59 on page 460. A plane has 2 dimensions, right, because it's kind of like a flat thing, extends infinitely, infinitely and has 0 thickness. Okay. How many non-parallel vectors, which are parallel to the plane, do you need to define the orientation of a plane? 2. You can also define the orientation of a plane if you have one perpendicular or normal vector. Okay, so for example, can you imagine if you had like 2 non-parallel vectors and you put them end to end like that, or you put them like that, and then you defined a plane that contained both vectors? Then you can see that you have defined the direction of the vector. Or if you have a normal vector, you can also define immediately the orientation of the plane, because it would sit perpendicular in all directions to the normal vector. Okay, this is kind of interesting. When you define all the points which make up a plane, you can use the following definition, which is pretty cool. You can use a position vector, and then you can add up any combination of 2 vectors which lie on the plane multiplied times like scalars. So you could multiply them times lambda and mu, for example. Okay? And the way that works is, look at this picture down here. So, let's say that you have a point defined, which is point A. And then you want to define every single point that's lying on this surface. Well, if you have two vectors that are not parallel, you could use these 2 vectors to like kind of scan out every single point on the plane by multiplying these 2 vectors by a scalar and making them various lengths, and then it would like access every single point on this tabletop here. And if I was to think of kind of an analogy for that, think about those little robot vacuums that like vacuum your whole living room. Not that I have one, but if you've seen those work, basically like sweeps out every single little spot on your living room so that it vacuums it, right? So, and all it does is like go, left, right, and forward, backward, and like in those 2 directions, it can literally vacuum your whole floor. And that's what these vectors would do. If you have 2 vectors, one that goes like horizontal, left, right, and the other one goes forward, backward, you can move your vacuum cleaner to every single spot on the living room floor. And that's kind of how it works. Okay, I don't know if that made any sense, but that's kind of the way I think about it. Okay, so if you define this here is like another way of defining it, which is you define a normal vector which is perpendicular to the plane, okay? And you could say, well, if I define a normal vector, I know that any vector which is lying on the plane must be scalar product of 0 with that normal vector. So I have the normal vector, and then I have any vector lying on the plane. The way I define any vector is I have x, y, z as like the point, any point on the plane, and I subtract out the one point on the plane, which is x1, y1, z1. And so then I create a vector like that, and then I scalar product with the normal vector, and that gives me 0. Okay? So if I was to expand this, I would say I would have a times x minus x1 plus b times y minus y1 plus c times z minus z1 equals 0. And then, so maybe if I was to expand it further, I would say ax plus by plus cz is equal to ax1 plus by1 plus cz1, where x1, y1, and z1 are a point on the plane, right? And a, b, c are the components of the normal vector. So that's kind of a cool equation too, right? So I'm going to write it down here. ax plus by plus cz. That's pretty cool. Find the equation of the plane with normal vector 2, 1, negative 1, 3, which passes through negative 1, 2, 4. This is really easy to do because we know that if we have one point on the plane, we could basically say that that's x1, y1, z1. If we have a normal vector 2, negative 1, 3, we could define that to be a, b, c, and we've already defined our equation. And here, I'm going to set it equal to 2 times x1 minus 1 times 2 plus 3 times 4. See how that works? And then, now I'm going to simplify the right side a little bit. I can actually reduce it down to a constant, right? So I'm going to leave the right side like that, and then the left side is going to become negative 2 minus 2 plus 12, which is equal to 8. Okay, last thing is I'm going to write the equation of a plane, which contains point 3, 2, 1, and this line, 1 plus t, 2 minus t, and 3 plus 2t. Okay, so, C, it gives me a point in the plane, and it gives me a line in the plane, written in parametric form. So, first thing I'm going to do is I'm going to see if I can change these two pieces of information into two lines that are both in the plane. And I think I can do that because, let's see, I have one vector which I could find, which would be, let's see, I'm going to change this into a vector form. So I'm going to have x, y, z is equal to 1, 2, 3 plus lambda times 1, negative 1, and 2. Okay? And so if I have this, do you see how I now know a second point, which is also in the plane? And if I have 2 points in the plane, I can make a vector, which is between the 2 points, which is, we kind of define the orientation of the plane. So what I'm going to do is I'm going to subtract those two vectors from each other, and that is going to give me 2, 0, negative 2, and that is a vector which is lying on the plane. And another vector which is lying on the plane is 1, negative 1, 2. And with these two vectors, which are kind of like both lying in the plane, I can do a cross product and figure out the normal vector of the plane. Right? So what I'm going to do is I'm going to cross product 2, 0, negative 2 with 1, negative 1, 2, and I'm going to get, for the top element, it would be 0 minus 2, so it would be negative 2. And for the second element, it would be 4 minus a negative 2, which would be 6. And you would have to take the negative of that because the middle element is always a negative. And then the third element would be negative 2 minus 0, so negative 2. And so that's the normal vector, but to make it, as easy as possible, I'm going to scale this normal vector. I'm going to divide everything by negative 2, so it's a common factor, and then it becomes 1, 3, 1. Okay? Then I'm going to take the normal vector, and I'm going to use the this format here to write a plane equation. So I'm going to take the 1, 3, 1, and I'm going to multiply it times x, y, z, and then I'm going to set it equal to, the left side is going to be 1, 3, 1 times one of the points on the plane, which, let's use just 1, 2, 3, for example. Okay? So I'm going to put times 1, times 2, times 3, And so the left side of the equation will become 1 plus 6 plus 3, which is 10. Right? So our equation becomes x plus 3y plus z equals 10. Right? All right.